Hello, folks. In this chapter, we're going to be looking at optical diodes. This is chapter 3-4. We're going to be looking at optical diodes, and we're going to be looking at two in particular. It's going to be looking at an LED, which is a light emitter, and we're going to be looking at a photodiode, which is a light receiver or a light detector. So let's get started with this. The light emitting diode, we've used these right here. If you've been in a digital class, more than likely you've used these before. That is the same LEDs that we've used in that class. So one of the things that you're going to have to make sure that you know is this symbol for an LED. And you also need to know make sure you understand what LED stands for, a light emitting diode. Okay, so the basic operation of the light emitting diode is as follows. When the device is forward biased, electrons cross the p-n junction from the n-type material and recombine with holes in the p-type material. And this right here is stuff that we learned way back in chapter 1 when we was talking about p-n junctions. And that's why it says, recall from chapter 1 that these free electrons are in the conduction band and at a higher level energy than the holes in the valence band. The difference in energy between the electrons and the holes corresponds to the energy of visible light. When recombination takes place, the recombining electrons release energy in the form of photons. And we've already spoken about those way back in chapter 1. The emitted light tends to be monochromatic, which means one color. That depends on the band gap and other factors. A large exposed surface area on one layer of the semiconductor material permits the photons to be emitted as visible light. This process is called electroluminescence. So that is a couple things there. You'll need to make sure that you remember what monochromatic means, meaning one color, and electroluminescence. You'll need to know what that process is called. So you'll see that in a quiz. So it says various impurities are added during the doping process to establish the wavelength of the emitted light. So that's important. You need to know that as well, because the wavelength determines the color of the visible light. And we'll see that in a chart here shortly. It says some LEDs emit photons that are not part of the visible spectrum but have longer wavelengths and are in the infrared portion of the spectrum. Okay, LED semiconductor materials. The semiconductor gallium arsenide was used in early LEDs and emits IR radiation, which is invisible. The first visible red LEDs were produced using gallium arsenide phosphide, on a GaAs substrate. The efficiency was increased using a gallium phosphide substrate, resulting in brighter red LEDs and also allowing orange LEDs. So we all know that now there's multiple colors in LEDs. We know that you can actually get some LEDs that you can actually have one LED and you can get multiple colors out of that. So, things are changing drastically as technology grows. So it says later GAP was used as the light emitter to achieve pale green light. By using a red and green chip, LEDs were able to produce yellow light. The first super bright red, yellow, and green LEDs were produced using gallium aluminum arsenide phosphide. By the early 1990s, ultra bright LEDs using indium gallium aluminum phosphide were available in red, orange, green, and yellow. Okay. And we keep going on. Blue LEDs using silicon carbide and ultra bright blue LEDs made of gallium nitride became available. High intensity LEDs that produce green and blue are also made from indium gallium nitride. High intensity white LEDs are formed using ultra bright blue GaN coated with fluorescent phosphors that absorb the blue light and re-emit it as white light. Okay, this is something that you'll need to know, is that the LED biasing, because we know it's forward biased. So let's look at the voltages that it takes. So right here it tells us what voltages. It says the forward voltage across an LED is considerably greater than for a silicon diode. Because if you remember, a silicon diode is 0.7 volts to forward bias it. So it's typically the maximum VF, forward bias voltage, for LEDs is between 1.2 volts and 3.2 volts, depending on the material. Reverse breakdown for an LED is much less than for a silicon rectifier diode. 3 volts to 10 volts is typical. So that 1.2 volts to 3.2 volts is something that you'll need to know. All right. So it says the LED emits light in response to a sufficient forward current, as shown in figure 330A. The amount of power output translated into light is directly proportional to the forward current. So basically that means, the more forward current, the more light. An increase in IF corresponds proportionally to an increase in light output. The light output, both intensity and color, is also dependent on temperature. Light intensity goes down with the higher temperature as indicated in the figure. Okay, light emission. LED emits light over a specified range of wavelengths, because we learned earlier that wavelengths, depending on the wavelength, determines the color of the LED. And as indicated by the spectral output curves in 331. So let's go up here and let's take a look at what this right here is on the next page. So this right here is kind of showing us the light output at the different wavelengths. So if you see, this right here is where this blue would peak at about this 460 nanometers is what that's in for the wavelength. And then it starts crossing over into green. Once we start bringing the wavelength up a little bit, it's going to start, this color is going to start going down, and it's going to start kind of turning green. And it's going to peak out right here about 540 nanometers and so forth. You can see the yellow and then the red. Then over here you can see that when you get up around 940, then you start going into infrared. Or actually lower than that, you start going into infrared, but you'll see where it peaks at, around 940 nanometers. Okay, so it says the graphs in figure 332, which is right here, show typical radiation patterns for small LEDs. It says LEDs are directional light sources, unlike a filament or a fluorescent bulb. The radiation pattern is generally perpendicular to the emitting surface. However, it can be altered by the shape of the emitter surface and by lenses and diffusion films to favor a specific direction. So what that tells us is that, these right here are usually, pretty much it's going to be more focused on a point or a direction. It's not going to be spread out unless you do what it says here, unless you have altered the shape of the emitter surface or some type of other altering device to make it spread out. So you'll see here that this right here is pretty much don't really fan out at all. But you can actually alter the lenses and things to make it span out over a wide area. But that's not typical. They're normally going to be really focused in one direction. It says directional patterns can be an advantage for certain applications such as traffic lights, where the light is intended to be seen only by certain drivers. Because I don't know if you've seen it before, but they also have like the little, on the traffic lights, they have like the little shield kind of around the traffic lights. I don't know, sometimes it may be just to keep snow or rain or something off of them. But the other thing is sometimes if you ever seen one blow around and you're in the cross traffic lane and you're stopped, you'll actually see those lights, and normally you can't see them. So what I'm getting at is that you only want to make sure that the other traffic coming other ways, normally ain't able to see them as well. You want to make sure that the lanes that they're in the direction that you're traveling, that's the lane that makes sure that you see them. So that's pretty important. So it says typical small LEDs for indicators are shown in 333A. In addition to small LEDs for indicators, bright LEDs are becoming popular for lighting because of their superior efficiency and long life. And I can tell you this, that that they are a lot more efficient. It is cheaper to run LEDs, and they last a lot longer, a tremendous amount longer than incandescent bulbs. So I know that where I work, we've changed a lot of indicating pilot lights on our control panels to an LED style bulb. So it says a typical LED for lighting can deliver 50 to 60 lumens per watt, which is approximately 5 times greater efficiency than a standard incandescent bulb. LEDs for lighting are available in a variety of configurations, including even flexible tubes for decorative lighting and low wattage bulbs for outdoor walkways and gardens. So I'll just show you here. This is the typical LED here that you'll see like in your digital class, is this one right here. And here's just showing you, like, there's LEDs, and like they are constantly changing the shapes and sizes and the LED, where the LED can go. I know back several years ago, they was kind of limited on certain fixtures and things that certain LEDs would go in. But as time goes on, you can almost get an LED bulb to go on almost any type of fixture, depending on a certain shape, whether it be a decorative type shape, a bulb or what. But that's that's where it's going to go, is trying to conserve energy, and also it lasts tremendously longer. So let's take a look at let's review some of the things that I think you're going to need to know for for at least a light emitting diode. So we're going to talk about the basic operation. Some of the things you'll need to know for sure are going to be that it's a forward bias. Okay. We're going to say electrons cross the p-n junction. From the n-type material and recombine with holes in the p-type material. Okay, the recombination of electrons release energy in the form of photons. Emitted light tends to be monochromatic, and photons are emitted as visible light through electroluminescence. Various impurities are added during the doping process to establish wavelength of the emitted light and wavelength determines the color of visible light. And the last thing is the bias voltage equals VF, and that there is 1.2 volts 3.2 volts. All right. And we also know that, move this over. We also have to make sure we know what, let me do that again, a diode symbol looks like. Or an LED diode, let me say that. It won't look as shaky as that, but it'll look something like that there. And again, you'll have the positive and negative side like that. So you just need to make sure that you know what the symbol is for that. You need to know at least these basic operations. And I tried to, as we went through the lesson there, tried to let you know some of the things that you would have to know for sure. So that is a light emitting diode. Okay, so let's go on to the photodiode, because the one emits a light, and the photodiode, which is on page 144, actually receives light. Let's see, 144, there we go. Okay, so the photodiode, and you're going to see two different pictures here. So this right here looks really similar to an LED, except you'll have the arrows that's pointing in towards the diode itself. That means that it's going to be receiving light, because the LED has got the arrows turned around where the light is going away from the diode, shows that it's emitting light. Another symbol is right here, looks like a little lightning bolt coming into the diode. So either one of these right here can be represented or represent a photodiode. And you may not know, but a lot of places, you know, if you have lights that turn on and off, have sensors or whatnot, that's like a dusk to dawn light, you will actually have a photodiode in that, and that's what's turning that light off and on. So the photodiode is a device that operates in reverse bias, as shown in figure 3-44A. It says where I is the reverse light current. The photodiode has a small transparent window that allows light to strike the PN junction. If you remember, in the PN junction, or like many things, that, you know, you're going to be able to, if you have a voltage, you know, or some type of external excitation, that's going to get things to moving. So here we have light, which is an external source of energy. It's going to strike the PN junction. So some typical photodiodes are shown in figure 3-44B, and an alternate photodiode symbol is shown in figure 3-44C. So right here is what it's talking about, this area right here. Okay? And it says, recall that when reverse biased, a rectifier diode has a very small reverse leakage current. The same is true for a photodiode. The reverse bias current is produced by thermally generated electron hole pairs in the depletion region, which are swept across the PN junction by the electric field created by the reverse voltage. In a rectifier diode, the reverse leakage current increases with temperature due to an increase in the number of electron pairs. A photodiode differs from a rectifier diode in that when its PN junction is exposed to light, the reverse current increases with the light intensity. When there is no incident light, the reverse current is almost negligible and is called dark current. So that's something you need to know is about the dark current. An increase in the amount of light intensity, expressed as irradiance, produces an increase in the reverse current. From the graph in figure 3-45B, you can see that the reverse current for this particular device is approximately 1.4 microamps at a reverse bias voltage of 10 volts with an irradiance of 0.5 milliwatts per square centimeter. Therefore, the resistance of the device is RR equals 7.14 mega ohms. So in this picture here, you can see this right here. It says that it illustrates the photodiode allows essentially no reverse current, and it says when there is no incident light. So this right here is showing us that when there's no light, let's just say if the sun is, if it's dark outside, then there's no current. If there's light on, let's just say if the sun has come up, then there is current. So this right here is going to turn things off and on. Okay. When a light beam strikes the photodiode, it conducts an amount of reverse current that is proportional to the light intensity, irradiance. So let's think a little bit about the photodiode. Okay. So let's talk about some of the basics on a photodiode. It operates in reverse bias. It has a small transparent window that allows light to strike the PN junction. Reverse biased current is produced by thermally generated electron hole pairs in the depletion region which are swept across the PN junction by the electric field created by the reverse voltage. All right. So the last thing we need to know about a photodiode is just to make sure that we know what the two symbols that you might see at some point in time. The one is going to be just like the LED, except you're going to have two arrows pointing in. The other one is going to be one that shows like a little lightning bolt, like that. So there'll be a short quiz after this right here, and then we'll get on to the next lesson. All right, thank you.